So far, we've looked at a variety of redox reactions or reduction reactions so far, right? But we also need to look at some oxidation reactions. Oxidation reactions can be done by carrying out reactions that increase the number of carbon electronegative bonds or decrease the number of hydrogen bonds. And again, in organic chemistry, we understand that both redox and oxidation happen, but these are classified as oxidation reactions because of what's happening to the organic compound here. We have two types of oxidizing agents in this section that we're going to talk about. One is chromic acid, which can be shown here being synthesized from chromium trioxide with sulfuric acid or sodium dichromate with sulfuric acid. Both of these a lot of times are made in situ, where you make these and then you add what you're trying to reduce. Okay, so the oxidation state here of chromium is +6. And we see this generally in in three forms. When we're looking at reactions, you can see it as CrO3, you can see it as chromic acid, or you could see it as sodium dichromate. Now, a chromic acid oxidation was historically also called a Jones oxidation after the Welsh organic chemist Sir Elwert Jones, who lived from 1911 to 2002. And what happens here is it will oxidize a primary or secondary alcohol with chromic acid acting as the oxidizing agent. And so we can see an example here where we have a secondary alcohol being oxidized to a ketone. And so let's kind of look at that mechanism. And so when we look at this is a partial mechanism. And so what you're going to see here is at first the OH here is removed. Okay. And we are just going to represent this as several steps, right? And then what happens here is it forms a chromate ester where the chromium complex is bonded to the oxygen. Then it undergoes an E2 reaction where these electrons come and steal that proton, and these electrons go here to form a double bond. And so this is classified as a chromate ester. Now, I want to point something out here. Notice that 2 hydrogen atoms must be removed. Okay? One is removed here, and then the second one is removed from the carbon attached to the hydroxide group. Okay? So that means if you have a tertiary alcohol, a tertiary alcohol cannot undergo oxidation with the chromate. So, for example, notice here, right, we have to have this hydrogen be removed. Tertiary alcohol has no hydrogen attached to this carbon, so there's really no way it can be removed. Now, the primary alcohol, on the other hand, has 2 hydrogens attached to that carbon. And so what happens here is you end up with a carboxylic acid as opposed to the ketone of the secondary alcohol. So if you have a primary alcohol, it's going to be oxidized to a carboxylic acid here. Now, when we look at this equation, what happens is we have an aldehyde formed kind of as here after the chromate, right? And then water is present in solution. And what will happen is the aldehyde will undergo an equilibrium with its hydrate. Okay, so this is in equilibrium. Now, when it undergoes and forms in this equilibrium, this hydrate, it can then go on to react with the chromate, and that's how we get the carboxylic acid. So it goes back and forth here, but as we form this, it reacts. Okay, and so we shift the reaction that way. Now, another oxidizing reagent that we can use is Pyridinium Chlorochromate. And one of the reasons we'd want to use it is if we look here, water plays a big role in this, okay? And we might want this oxidation to stop at the aldehyde stage, right? And so if that were the case, we can't use chromic acid because chromic acid is going to go all the way over here to carboxylic acid because there's water present. But I want you to notice when we use pyridinium chlorochromate or PCC, we stop here at the aldehyde stage, okay? So this will oxidize a primary alcohol to an aldehyde. It will also oxidize a secondary alcohol to a ketone. Now, PCC, I want you to look at this. It contains the same chromium 6+ species as chromic acid, okay? So oxidation is possible when the OH group is attached to the carbon atom bonded to a hydrogen. But unlike chromic acid, PCC is soluble in non-aqueous solvents. So this is a non-aqueous solvent, right? Which it's dichloromethane, and that allows the oxidation to take place in the absence of water and us to stop at the aldehyde stage. So I want us to do an example. Okay, we have this synthesis, and it says, show how to carry out the following synthesis. Now, whenever we start this, we need to analyze what is going on here. So when we look at this synthesis, we need to ask ourselves, does the synthesis require the formation of a carbon-carbon bond? And which carbon-carbon bond? And so what we're going to notice here, right, is these atoms, right, are here, correspond to these atoms here, okay? And these atoms here are the part that's different, okay? So we are going to form a carbon-carbon bond right there. Okay, so we do require the carbon-carbon bond, and we've identified which carbon-carbon bond it is. Okay, so we can kind of view that's kind of how we could cut that. Okay, and so have we learned a reaction that will form a bond like this and leave us with a ketone? Okay. If not, can the ketone be produced from the product of another carbon-carbon bond forming reaction? Now, the ketone could be produced from the oxidation of the corresponding alcohol, right? Which could happen after we do a Grignard reaction, okay? So what we're talking about there is if we think about this in reverse, and we are going to cut this sucker right here, right? We could say, okay, hey, look, let's undo the oxidation. And so if we undo the oxidation, now we have that guy there. And then if we undo a Grignard, which is one of the ways that we know to make a new carbon-carbon bond, then this is what we would have. Okay, so now we need to think about this in the forward direction. So how can the aldehyde be produced from a starting alcohol? And so to do this, we would need PCC, right? Because we don't want, right? That would be we don't, PCC would be a viable option here. Because the first oxidation, because we're really doing two oxidations, okay? Because right, we need to get this. This is not the starting material that was given. We need to get it to here, okay? So this guy right here is a primary alcohol, okay? So we're starting with a primary alcohol. Now, this guy here is a secondary alcohol. And so we can use chromic acid for that, right? But for primaries, if we need it to stop here at the aldehyde, we have to use PCC to do this, okay? So what we're going to do is, let's write this in the forward direction. We're going to say, okay, hey, look, we're starting with the starting material that's given, right, which is a primary alcohol. And we think about the reagents we need. And so we know we need PCC because we don't want there to be any water. Because if there's water, it won't stop at the aldehyde. And that's what we need this to do. Then, with an aldehyde, now we can add our Grignard. Right? And when we add our Grignard, now we have a alcohol group and we formed a carbon-carbon bond. Now we can go on and use the chromic acid and form the ketone there. So, this would be an example of PCC and both chromic acid being used in a synthesis. Now, another common oxidizing agent is potassium permanganate, which is KMO4. Potassium permanganate shown here. It's an ionic compound with the potassium cation, K+, and the permanganate anion, which is MnO4-. Structurally, the MnO4- does resemble the chromic acid here. In both compounds, you have a central metal atom that's bonded to 4 oxygen atoms, right? And so what this does is it gives the metal a high positive oxidation state. So manganese, for example, has +7, and the chromium in the chromic acid has a +6. So, like chromic acid, potassium permanganate can be used to oxidize alcohols. And it's shown, we've got some examples shown here in 2023 and 2024. Now, when treated with a basic solution, so we've got a basic solution, potassium permanganate, what happens here is you treat it with potassium permanganate, you stop it, and then you do an acid workup. So it's a sequential reaction. And what we see here is we have a primary alcohol, right, and aldehydes are oxidized to carboxylic acids. And then secondary alcohols are oxidized to ketones. So primary alcohols and aldehydes. Right? And that's the same outcome that we see with chromic acid as the oxidizing agent. It may seem that potassium permanganate and the chromic acid are interchangeable, but they aren't. And the reason they're not is because H2CrO4 is more selective than KMNO4. And we're going to look at this more in chapters 24 and 26, but KMNO4 can oxidize a variety of compounds in addition to alcohols and ketones. So it can also oxidize things like alkenes and alkynes and alkyl benzenes. So you really have to watch when you use KMO4 that you don't have like gobs and gobs and gobs of other things, other functional groups that can also be oxidized as well.